What on earth is this transcript? Okay. Right, so like I said last week, we discussed types of equilibrium points, okay, of the linearized system next to or around in the neighborhood of the equilibrium point, okay, and those behaviors of the system around of the linearized system, yeah, of the different object, the error system actually around the equilibrium point was showing us the behavior of the nonlinear system, okay, or gave us most indications about the behavior of the nonlinear system around that specific equilibrium point, okay, and essentially the behavior is identical, okay. And we found out that next to the equilibrium point, for very small variations, we have behaviors such as focus, node, saddle point, okay, and sometimes center. And we were discussing about the stability of the structure of such points. And we realized that the nodes and the foci, that's the plural of focus because focus is a Latin word, okay, and words in Latin receive the plural as in Latin. That happens in English, okay. So focus, foci, okay. Um, these are structurally stable. That is, if any disturbance, any perturbation of the A matrix from X dot is AX shows up, that disturbance is not changing the types of equilibrium points. Why? Because essentially the eigenvalues of such systems are continuous functions of the elements of the matrix. That's why. Okay? And any perturbation keeps this continuity. The only problem is that when you talk about center behavior, so when the linearized system has eigenvalues strictly on the imaginary axis, those eigenvalues are not actually on the imaginary axis. Okay? Essentially, their neighborhoods are not behaving. So the imaginary parts, okay, you have here. So their neighborhoods are not only these segments, okay, but they are these disks. These disks. Hence, um, the imaginary axis eigenvalues can easily get a non-zero real part, either to the left or to the right of the imaginary axis. Okay, of course they are synchronous in some sense. That is, if one of them gets negative, the other one also gets negative. Okay, so in this respect, if you look at this picture, in this respect, okay, let me just delete what's not useful here. Okay, in this respect, these points, this structure is not stable. This structure, but this structure is stable. I mean, look at the balls. They are still points of the same type with a specific real part, negative or positive or whatever. So if you have a node, even if your system is subject to some perturbation, to some parametric perturbation, the resulting equilibrium is still a node. Or if it's a focus, it's still a focus. Well, if it's a center, then your points may migrate in this direction. So from a center behavior, it can easily become a stable focus. That's the lucky part. That's when you get lucky. But usually you get unlucky and the eigenvalues migrate to the right of the imaginary axis. This is much easier for them to do. And physics confirms that because instability is much easier to obtain rather than stability. Okay, that's a simple principle, an axiom actually. Okay, so they become unstable foci or an unstable focus. Hence, the center behavior is not a structurally stable behavior. That is, the structure is not stable. Okay, the structure itself is not stable. Okay. And here we had the proof of that with the A plus delta AX system, and we proved what happens with perturbations of the type delta. For instance, for this matrix, yeah, this matrix has the eigenvalue, so the spectrum of this matrix is plus minus J. Okay, this is a rotation matrix. This is a matrix with complex eigenvalues. So this is plus minus J. So if you make it delta, then A becomes delta minus 1, 1, 0. Assume data is a real number. Actually, data is a real number. So the eigenvalues of this guy, let's call it A tilde. The eigenvalues of A tilde are what? Are sigma plus minus J. Are sigma, not sigma, delta, sorry. They're delta plus minus J. They're delta plus minus J. You see, delta. So now they become, and if this is positive, then it becomes an unstable focus. An unstable focus. Okay? So this structure is not stable. Okay? Is a stable or unstable focus depending on the sign of delta. I assumed here delta was positive. However, you may easily assume delta were negative. Okay. Okay, and then you get this. I left you this for homework to determine the largest value of alpha for which this is still stable. Well, in this case, it's not very difficult, but it's a difficult problem in other senses because you have to do some optimization. Okay, so the characteristic equation of this matrix is lambda squared plus 2 lambda plus 1 plus 1 plus alpha, okay, or not, plus or minus, sorry, minus 1 minus alpha, minus 1 minus alpha is 0, so that's lambda squared plus 2 lambda minus alpha equals 0. So you need alpha negative, first of all. If you want this to be stable, alpha should be negative. Alpha should be negative, okay? And then you have to try to determine the largest value of alpha to keep this, to make this a stable focus. To make this a stable focus, that is, the eigenvalues here are lambda 1, 2. They are minus 2 plus minus delta is 4 plus alpha, right? No, sorry, 1 plus 4 alpha. 1 plus 4 alpha. Okay? Divided by 2. These are the eigenvalues. Okay? These are the eigenvalues. Because they're product. So, is this correct? Because lambda 1, lambda 2 is minus alpha. Now 1 plus lambda 2 equals 2. Okay? Something like that. No, this is not right. B squared, that's 4 actually here. No, this is correct. Okay? So this is essentially minus 1 plus minus. Okay, you want this to be complex. So you make it here J plus minus what? Like this, right? And you want, first of all, delta to be negative. You want delta squared to be negative. Delta squared, you want it like this because you want to focus. Okay, so that is 4 plus 4 alpha is negative. That's alpha, right, less than -1. So alpha should be less than -1 if you want to have complex conjugated eigenvalues. And these are your complex conjugated eigenvalues. Okay, so if you add them up, the sum is -2. Is -2. Sorry, is -2, and their product should be -a because of j. -a because of j. Okay, and then of course you have to find the values of alpha for which is a stable focus. Okay, so first of all, alpha is -1. Stable, it's forever because of this -2 here, right? So it can be fixed. And you can investigate this. You have here a small sketch. You can further investigate this. Okay. So finally, we were wondering ourselves, how do the systems behave when you add the higher order terms? Okay. And the conclusion is that one can rigorously prove that in a sufficiently small neighborhood of the equilibrium point, the trajectories of the nonlinear systems, they are very close to the trajectories of the linearized system. So they look the same. That's the idea. Even if both or each of these or the nonlinear system is totally different from its linearized error counterpart, deviation counterpart. Okay. But this property holds only for structurally stable equilibrium points. That's the big idea. For the stable and unstable node or saddle, or for the saddle point, or the stable and unstable focus. For the case of the center, you don't know what happens to the nonlinear system. So essentially, this behavior center, this is the behavior of the linearized system, is undecidable for the nonlinear system. You can't decide whether that is a stable or an unstable equilibrium point. You can't tell. Because of this perturbation analysis we showed earlier. You don't know if the disturbance in the real part is negative, or so is to the left of the imaginary axis or to the right of the imaginary axis. You can't control that, essentially. You cannot control that. Hence, you can't decide. It's undecidable in this case. Okay. So you can find the qualitative analysis or draw qualitative conclusions of the behavior of the nonlinear system around the equilibrium by linearizing. So linearization is good. Okay. Okay. So provided the origin is a structurally stable point for the linearized system, you can draw the same conclusion about the nonlinear system. Okay. Examples. Let's see some examples. Figure 2. I'm trying to find what figure 2 is. Figure 5. The mechanical system in figure 2. What is figure 2? You know? Oh, this one. The mass spring damper system. Okay? With this function. Okay? So you may take a soft spring. Okay? A soft spring. So that's the soft spring is ky times 1 minus a squared y squared for absolute value of ay less than 1. This is a soft spring. Okay? This is a soft spring. Okay? So let's look at the equations of this guy. Okay? Let's look at the equations of this guy. So you have Let's see if we can do a little bit of this example just to make a sketch of it. Okay. So it's my double dot plus by dot. This is the friction, linear friction, plus ky times y1 minus a squared y squared equals 0. Okay, we make no exogenous effort on this guy. We don't force anything. Okay, so then this becomes if you divide by the mass, so you get x1 equal x2. Okay, so we just write the F now, x2, and x2 dot equals minus b over m x2 from this term minus k over m x1 times 1 minus a square x1 square. Okay, I'm going to write this once again to make it prettier. So is minus k over m y times 1 minus a y. We don't have y here, we have x1. A square x1 square minus b over m x2. Okay, so this is my mechanical oscillator. My mechanical oscillator. Okay. Right. Oh, I have a phone call. Who called me? Excuse me a second, please. Oh. Right. Okay. So who is F? So this is x dot is fx. F x is x1, x2, and fx is, this is x, fx is x2 minus k over m x1 1 minus a square x1 square x1 square minus b over m x2. Okay, this is F. And then the Jacobian, the equilibrium points. Okay, equilibrium points or EP, short, equilibrium points, x2 equals 0. And then we have the second equation becomes minus k over m x1 times 1 minus x squared x1 squared 0. And then you get several solutions here. The first one is x1 equals 0. So the origin is an equilibrium point. Okay. The second x1, then you get the second equation. 1 minus a squared x1 squared is 0. This is equivalent to a squared x1 squared is 1, which is equivalent to x1 squared is 1 over a squared, which means that x1 is plus minus 1 over a. Plus minus 1 over, of course, absolute value of a, actually. Okay? Agreed? Agreed, yeah? So we get 3 equilibrium points, okay? 0, 0, and plus minus 1 over A 0. True? Is this correct? Should be, huh? Should be. We have 3 equilibrium points, so if you were to draw the phase portrait of this guy, so we have 3 equilibrium points. Assume A is positive. Minus 1 over A, 1 over A, and 0. And 0. Interesting, huh? 3 isolated equilibrium points. So we can easily understand that probably we have 2 stable equilibrium points and an unstable one. Or the opposite, we have a stable equilibrium point and 2 stable to unstable equilibrium points. This is the only way we can have it. This is the only way we can have it. Okay? This is the only way we can have it. And what happens now? You have to compute, we have F here, so we have to compute the Jacobian of F. Okay, which is 0, 1 for the first one. And then for the second one, we have what? Minus 4a squared x1. No, this is not good. Delete. Because this is minus k over m x1 minus plus k over m a squared x1 squared x1 to the power 3. True? So you get 3k over m a squared x1 squared minus k over m. True? And here you just get minus b, not b, we call them b, minus b over m. Okay? So this is the Jacobian. Now you have 3 equilibrium points. So we get 3 dynamics. 3 dynamics. Okay? So we get the linearized dynamics is x dot is ax. And we have a equal df dx evaluated in the origin. That's 0, 1 minus k over m minus b over m minus b over m. Okay. So I'm just following the entire analysis we did last week and we finish now. Okay. The characteristic equation is lambda squared minus b over m lambda. And the determinant is no, sorry, this is plus k over m equals 0. Okay, now, since m, b, and k are all positive, then pa lambda is lambda squared plus b over m lambda plus k over m is a Hurwitz polynomial. Hurwitz means that the roots lambda 1, 2, they are all in the complex left half plane. Hence, this is stable. This is stable. Stable. It's stable. The origin is a stable point. The origin is a stable point. That means it's an attractor. The trajectories nearby are drawn towards the origin. The trajectories are drawn towards the origin. Now let's see about the equilibrium points. Delta. Delta is b squared minus 4AC. Agreed? B squared over, okay. So this is what? Then we have the cases. If this is larger than 0 or negative. Okay? So when the friction coefficient, this is equivalent to B squared over M squared larger than 4K over M, M goes away. So that means that B squared over 4M is larger than K, the elastic constant. Then you get what? You get two stable nodes. Nodes, because they are all, this is a Hurwitz polynomial. Again, this is a Hurwitz polynomial. Check the Hurwitz criterion. Do you know the Hurwitz criterion? Have you heard about it? Have you heard about the Hurwitz criterion? Yes.
From
That's the one.
DSA during our second year.
Yeah, but I'm sure you used it all along. Okay, so I just remind you, if you have a polynomial, I'm just exemplifying for the second degree. Okay, so if no, so definition. Okay, a polynomial is Hurwitz P of degree 2. Of degree 2 is Hurwitz if and only if all the coefficients have the same sign. So the Hurwitz, what's it saying? If you have P lambda is lambda squared plus A lambda plus B, the Hurwitz matrix is this guy, A, 0, 1, B. That's how you build it. This is the Hurwitz matrix. Hurwitz matrix. This is the Hurwitz matrix. And the Hurwitz criterion, okay? So if A is positive and also the determinant of the matrix is positive, equivalent to AB positive, then P lambda is Hurwitz. Okay, again, equivalent to the roots are in C minus. Okay, in C minus. So as you can see from this proposition, essentially the coefficients are not allowed to change the sign. So this is what happens with this polynomial. It's not changing the sign. Okay, so its eigenvalues are automatically in the complex left half plane. However, they can be real roots, or if this is negative, which is equivalent to K larger than B squared over 4M, then you get two stable foci. No, sorry. No, two stable eigenvalues. No, it's a 1. It's a 0, 0 is a stable node. No, it's 1. It's only 1. It's a stable node. And here 0, 0 would be stable focus. Stable focus. So essentially, if you go back to this plot, let's go to the focus. Around this point, you get this type of behavior. You get this type of behavior around this point. You get this type of behavior. Okay? Right. But then, this is one situation. The second situation is A is df for the other equilibrium points is df dx in plus minus 1 over a 0. And you substitute this, okay? You substitute this, you get a equal to 0, 1, 0, 1. A squared and a squared, they go away. So 2k over m minus b over m. The sign changes. Sign changes. Then the characteristic equation in this case is lambda squared plus b over m lambda. But this time it is minus 2k over m equals 0. Okay, so not Hurwitz. Not Hurwitz. Okay, that means you get 2, or at least 1 unstable root. 1 unstable root. So they can be both unstable or stable roots. Okay. And if you go further with this, with the analysis, if we can go further with the analysis, we'll see that actually these 2 points can be saddle points. They can be saddle points. If you remember, they are saddle points. And if you take their eigenvectors, look what you find. You find this called separation area. This is called separation area. Separation area. It's called the separation area. And the behavior of the system, if it's in this separation area, it veers off from the unstable equilibrium points and goes to the stable node. This is the behavior of a mass spring damper system with a soft spring. Okay. We are going to do this analysis once again to explain this notion of separation. Separation. Okay. So this is interesting. That's one thing. The second example is this polynomial system. When you go to polar coordinates, and we proved this last time, if you remember, if you go to polar coordinates, what's polar coordinates? I remind you, x1 is r cos theta, x2 is r sine theta. This is polar coordinates. It's a nonlinear coordinate transformation. Okay. Polar coordinates. And if you substitute this and you do some calculations, not very complicated calculations, but you just have to be careful where the terms are just canceling each other. Okay. But you can do that very easily. You end up with a differential system in polar coordinates, the radius and the angle, of this form. Please note that these equations are totally decoupled. They are totally decoupled. First of all, the angle is is constant, and the equation of the radius, if you look at this equation, so r dot is mu r times r squared minus 1, you get two equilibrium points for this equation, r equal to 0 and r equal to 1. R equal to 0 and r equal to 1. Okay? And you can easily check, you either plot fr versus r, or you just do the first order derivative. Okay? You just do the first order analysis, and you'll find that one is an attractor and the other one is a repulsor. One of the points is a attractor and the other one is a repulsor, depending on the sign of mu. Depending on the sign of mu. Okay? Two equilibrium points, that's 0 and 1. The first one corresponds to the equilibrium in the origin. The other one is in the plane. The other one corresponds to a circular trajectory. You see that? For x. R equal to 1 is a constant radius. It's a constant radius. And this guy, the angle, is a constant. So it's constantly turning. It's constantly turning. Okay? But this is an isolated trajectory, the circular one, because r equal to 1 is an isolated equilibrium point. If mu is negative, then r equal to 1 is an attractor. Whereas if while r equal to 0 is a repulsor, and conversely, this behavior is changing in between them. And this is the way for the situation for r equal to 1 corresponds to what we call a limit cycle. If you remember, this is a totally nonlinear phenomenon. You don't get this. You do not get limit cycles for linear systems. Furthermore, limit cycle we're going to easily see is, since this is an isolated equilibrium, it's structurally stable. So the limit cycles are circular behaviors in the phase portrait, but they are structurally stable circular behaviors, not like the center. So limit cycle is totally different from the center. Please keep this in mind. Okay? So this is the limit cycle. Okay? So the correspondent of the equilibrium r equal to 0 is an unstable or stable focus. Is an unstable or stable focus. Okay? Theta is decreasing linearly. R equal to 1 corresponds in the x1, x2 plane to a so-called limit cycle. What is a limit cycle? A limit cycle is a closed and isolated trajectory defined by a periodic solution. It's defined by a periodic solution, of course, because it's a sine or a cosine. Recall that the function is periodic. Okay, so this is the definition of a periodic function. The question is the center a limit cycle? No, it is not a limit cycle. Okay? The center is a closed trajectory defined by a periodic solution, but it is not isolated. This is the problem. You remember the perturbation analysis we did earlier. That's not isolated. Okay? So in an arbitrarily small neighborhood of the center, there is another similar trajectory. So coming back to our example, notice that the limit cycle is stable for mu negative when r equal to 1 is an attractor, and unstable if mu is positive for r equal to 1 a repulsor, or r equal to 1 a repulsor. Okay, and when we plot, and we are going to see this in MATLAB or Maple, I'm going to show it a little bit later. This is the behavior. This is the behavior of this system. Okay, so this system is actually an oscillator. If r equal to 1 is stable, is an attractor, it means that our given polynomial system is actually an oscillator, and a stable, structurally stable oscillator. So it's not going to change its behavior under any kind of disturbance. Interesting, isn't it? Isn't it? Okay, let's have a short break and then we talk about the van der Pol oscillator. And we were supposed to have some theorems here, but I don't see them. 36. I'm trying to see where. So we have results about the existence or the non-existence of limit cycles. Okay. Let's have a short break, please. Okay, I'm back, so I hope you're still here. Van der Pol oscillator. This is a fully nonlinear system, and it's described by this differential second-order equation. And if you look very closely, this time the elastic force term is linear with an elastic constant 1, but this time the dissipation, if you look here, the dissipation is variable. So the dissipation becomes nonlinear. The dissipation depends on a coefficient epsilon, okay, as well as the derivative of some interesting function. Okay, this third order function, if you see here. Now, we can very easily rewrite this guy as a normal system, okay, as a first order system. So x1 dot is x2 dot is minus x1 plus epsilon times 1 minus x1 squared x2, okay. Okay, so this guy here, h prime v, this is derivative, this is minus 1 plus x squared, minus 1 plus x squared, okay, right? So this is easily substituted in this guy over here with a minus sign. Okay, so this is the Van der Pol oscillator. Equilibrium points, it can be easily seen that the origin is the only equilibrium point of this system. So we only have the origin, okay? If this is the phase plane, everything is going on in this guy. Is the origin, okay? Right. So let's see about the behavior of this system. So fx again is x2 and minus x1 plus epsilon times 1 minus x1 squared times x2. Okay. Then the Jacobian df dx is 0, 1. Epsilon times 1 minus x1 squared minus x1, and epsilon, no, this is wrong. This is wrong. This is totally wrong. So this is what again? Minus 1, okay, minus epsilon x1 squared. This is correct, true. And here on the other side, on the other part, you have epsilon times 1 minus x1 squared, okay? So this is the Jacobian, which means that if you write x dot is ax, the matrix A is df dx evaluated in the origin, and that is 0, 1, minus 1, epsilon, minus 1 and epsilon, with the characteristic equation, for the eigenvalues, lambda squared plus epsilon lambda plus 1 plus epsilon lambda plus 1 equals 0. Okay? So we have a discussion about epsilon now. Okay? Discussion on epsilon, real number. Epsilon, real number. First case, epsilon positive. That means that p lambda is lambda squared plus epsilon lambda plus 1 is a Hurwitz polynomial, which means we get two eigenvalues, lambda 1, 2, in the complex left half plane. So we get either a stable node or a stable focus, if epsilon is positive. This is the behavior. Okay? For epsilon negative, we get 0, 0 to be what? Epsilon is negative, so 1 will be positive. Probably, yeah, we get epsilon negative lambda 1, 2 is minus epsilon plus minus epsilon squared minus 4 divided by 2. Okay, epsilon is positive, minus epsilon is negative. Minus epsilon is positive, sorry. So essentially what you get here, you get a saddle point. For epsilon larger than 2. Okay, for actually absolute value of epsilon larger than 2. Okay, all right. However, this guy, so for epsilon negative, you can get this to be an unstable point. Okay, no matter what, you get this to behave like an unstable point. Okay, so where does the trajectory go if this is an unstable point? Where does the trajectory go? Okay, unstable. Where does the trajectory go? Where does the trajectory go? No, this is wrong. You didn't tell me. This is minus. Sorry. So for epsilon positive, for epsilon negative, this is true. It's totally different. For epsilon negative, it's like this. And for epsilon positive, we get this issue. So for epsilon negative, for epsilon positive, you get instability. Okay, you can have a saddle point, or you can have unstable. No matter what, you get unstable node or focus in this case. Everything is unstable because of the alternating sign here. This is not Hurwitz, because of the alternating sign. Actually, this is also minus. Why didn't you tell me? This is also minus. Okay. So now we have to do the analysis all over again. There must be something wrong. I'm just trying to do the analysis once again. Okay. Let's do the analysis once again. Yeah. Because there's something wrong about what we have just said. You have to be careful about these things, about the signs, because signs are crucial here. Okay, the signs are crucial this time. I'm just going to delete all this and start from scratch. Okay. So again, look at this matrix. The characteristic equation lambda squared minus trace is epsilon plus determinant, and determinant has a minus here. Okay, has a minus here. So it's -1. Okay. It's -1. And we have the discussion over epsilon. We have the discussion over epsilon. So for in any case, okay, so no matter, okay, so this is not Hurwitz. For all epsilon real, this is unstable. Okay. So that means for all, because it's changing the signs, even if epsilon is positive or negative, this guy is changing signs. So this is not Hurwitz. So that means that there exists root lambda somewhere in the right half plane. So this is an unstable behavior. It's unstable. Okay. So we get that for all epsilon, the origin is unstable, is an unstable equilibrium point. The origin is an unstable equilibrium point. How unstable or what type, we have to see now. So we can get, we have lambda 1, 2 is epsilon squared, delta, first of all. Delta, this equation. Delta is epsilon squared plus 4. So this is positive, true? For all epsilon. This is positive for all epsilon. This is positive for all epsilon. Hence, we get here lambda 1, 2 is epsilon plus minus square root epsilon square plus 4 divided by 2. Divided by 2. Right? So essentially, you can either get unstable node depending on the value of epsilon. Okay. Unstable node for epsilon smaller than square root of epsilon squared plus 4. Okay. But this can never happen, actually. Can it happen or not? No, it can't happen because it's plus 4. So this is actually, this is always larger than. This is always larger than. So you just get an unstable node. I thought it could be a saddle point, but that's not the case. That's not the case because both of these are positive for all epsilon. Yes or no? Or a saddle point. Well, anyway, unstable. Saddle point or unstable node. Saddle point or an unstable node. So where does the trajectory go then? Again, the question remains. Okay. Question. Where do the trajectories go? The question remains. Question remains. Probably we are going to have a limit cycle because it's an oscillator. Probably a limit cycle. How do I find out? That's the question. How do I find out there is a limit cycle? How do I find out? There are some theorems. There are some theorems helping us do that. Okay, so it's all very important to know if a system can have its own maintained, constant, persistent oscillations, undamped. Okay, irrespective of the disturbances it's been subjected to. The linear system cannot do that, but the nonlinear systems can do that. That's about the limit cycle. You can use this, for instance, in electronics quite a lot. Okay. The problem it says here for self-maintained oscillations for second-order systems is about the problem of the existence of limit cycles. The existence of limit cycles. The existence of limit cycles. Yeah. Of course, these curves. So you want to see if you can get this type of behavior. Okay, x1, x2. Of course, these curves are separating the phase portrait into two domains: an interior, the interior of the limit cycle, and the exterior of the limit cycle. The exterior of the limit cycle. Probably in the interior of the limit cycle lies an equilibrium point, you know. And we have a first theorem given by Poincaré, the French guy, and Bendixson. We have a first theorem saying that if the trajectory of a second order system is bounded for positive t, then there are three situations. A, the trajectory goes to a stable equilibrium point, or B, so you either go to a stable equilibrium point. Remember the Riccati equation from the previous chapter. Okay, the trajectory goes to a limit cycle, or it is a limit cycle. So if you have boundedness of the trajectory, you can have either of the three situations. You can't have anything else. Nothing else occurs except these three situations. Okay, so the trajectory is bounded. Okay, that means you get to some constant energy of the system. You either go to an equilibrium point, a stable equilibrium point, and we are going to use this for the Lyapunov stability analysis we are going to do in the next chapter, where you can get zero energy or constant value of energy throughout the time from a certain moment on, and that can be a stable equilibrium, or that is a stable equilibrium point. This is a sufficient condition to get us to assess or to find or to get the stability of an equilibrium point. And this is from physics. Imagine the pendulum. The pendulum is swinging and swinging until it stops. That's zero energy. But what happens if the pendulum is in a region where it's constantly swinging and never stops with a constant angular velocity? Well, that means you go not to an equilibrium point, but to a limit cycle, because you do not get constant energy, but you get constant variation of the energy, bounded. And that's a limit cycle. Okay? Okay? Can you understand a little bit of what I'm saying here? This, you have to imagine things getting physical. Can you imagine that? Hmm? Can you imagine that? Yeah. If I have the phase plane and I have the origin and the trajectory is bounded like this, so it either goes here, this is one situation, or it goes here, and this is a limit cycle, okay? Right? Or is the limit cycle itself, is this guy itself, the trajectory? Okay? This is what happens. Do people follow me?
Yes.
Okay. If you have questions, please stop and ask. Okay. So the question is now how to look for limit cycles. How to look for limit cycles? That's the question. So if you can put in the phase plane, in the phase portrait, or in the trajectory space, if you can identify a closed and bounded set invariant for all time, the solutions initialized there, they stay there. Remember the mechanical oscillator. Remember this picture. Where is it? I made you a very nice picture of the mechanical oscillator. This one. Okay. Imagine again this picture. Yeah? Imagine again this picture. So if this is a bounded set inside this parallelogram, or inside this geometric figure, okay, right? So if you initialize here, or you have the initial condition here, or here, or here, the trajectory starts inside. So even if you start here, close to this saddle point, it will push away. The system will push away, but will go to the focus or to the limit cycle, as we can see. Okay, this is always happening if you initialize within this bounded closed set. Okay, if this bounded closed set does not contain an equilibrium point. So imagine for the mechanical oscillator, if you had no equilibrium point, then so if you have no steady state, essentially, if you don't go to any steady state inside such a bounded set, you will you will definitely have a limit cycle in there. Okay? Think about it. If you take the previous example, where is the example? Not previous, but this example. If you take this example, okay, and you consider the energy of this guy. Okay, you consider the energy of this guy. You take the simple energy. You take the simple Euclidean energy. This is what? You can consider this the total physical energy, yeah, kinetic and potential energy. Okay, and you do the time variation of this energy. You do the time variation of this energy, and this is what? This is dv dx times x dot. Okay, Leibniz rule of derivation. We know that. Okay, because this is a scalar function of multiple variables. Okay, so v is defined on R2, taking values in R. Furthermore, note that V is an energy because V is always positive, is positive definite. Okay? So this is an energy. Energy is always positive definite, okay? If you take the time variation and you do the computation, this is what? This is x1 times x1 dot plus x2 times x2 dot. And if you substitute x1 dot and x2 dot from these equations, you get here twice mu times x1 squared plus x2 squared minus 1 times x1 squared plus x2 squared. So you notice that this variation, if mu is negative, this is negative for mu negative. This is negative for mu negative. So that means that the energy is decreasing. That means that the energy is decreasing. Okay? Yeah. The energy is decreasing because the variation is negative. Okay? But you can also have the variation to increase if mu is positive. If mu is positive, this is positive, and it will stop at some upper bound, say C1. Okay? And it will stop at some bound. It will stop at some bound where it becomes constant. Okay? So probably, and we know that this guy has a limit cycle. So based on this energy analysis, we can have to see where the limit cycle is. But we need other results because this is not also very clear. You cannot do every time this kind of analysis, but we can have some results. Okay, can have some results about results on the existence of limit cycles. Okay, let's stop for a few minutes and I come back and I show you these results, and then we are going to see some very interesting examples. Okay, see you soon. Sorry, I just got back. Okay. I was saying some results on the existence or the second one will be on the non-existence of limit cycles. So we have one theorem due to Poincaré or thanks to Poincaré, because the guy says if inside a limit cycle okay, there exists only structurally stable equilibrium points such as node, saddle, or focus. So if we only have that inside, then n equal s plus 1, where n is number of foci plus number of nodes, and s equal number of saddle points. Okay? Okay. And if you go back to the picture, if you remember the picture of the mechanical oscillator, yeah, you remember that picture? Yeah. Where you had this equilibrium point, this stable equilibrium point, and here you had the saddle points. You had two saddle points, okay, and one stable equilibrium point. One stable equilibrium point. Okay. All right. So inside the limit cycle. Inside the limit cycle. Okay. So you have 0 saddle points inside. The saddle points are outside the limit cycle. Okay. So you have only one. If you were to have a limit cycle in this parallelogram, okay, you had only n equals 0 plus 1, because you have two saddle points at the extremities and you have a focus or a node which is stable in 0. Okay, so this is one way to look at it. And the second way is the theorem of Bendixson. And the second one is the theorem of Bendixson. Okay, Bendixson. When limit cycles do not exist. And this is very interesting to see, because it says if in a simple convex domain, yeah, you have fx. Yeah, fx, remember, is f1, x1, x2, f2, x1, x2. This is your f. Okay, and if you remember, the Jacobian df dx is df1 dx1 df1 dx2 df2 dx1 df2 dx2, and you look at this like a matrix. Okay, it's not true, but this is how you look at it. Ax, you look at it like this. Okay, now it says if on this simple domain df1 dx1 plus df2 dx2 are non-zero, okay, and keeps the sign, maintains the sign plus minus along this domain, okay, along this domain, then there are no closed trajectories. Hence, there are no limit cycles. Okay? Do you understand? This is a nice condition to see whether there is or not a limit cycle for your system. And if you go back to the mechanical oscillator, wherever that may be, here, okay? Look at this. Look on the diagonal. Look on the diagonal. On the diagonal, you have these guys. These are never zero. These are never zero. And they can keep the sign because it's 1 minus b over m. Okay? So there is no limit cycle, essentially. There is no limit cycle. Okay? If you had a limit cycle, the Poincare theorem told you that the number of foci and nodes would be the number of saddle points plus 1. So that's 1. Okay? Well, the van der Pol oscillator. We go back to the van der Pol oscillator because we were left with this question. Okay, van der Pol oscillator. Yeah, van der Pol oscillator. Okay, so we remember that fx was something such as x2, and I don't remember by heart, but I can easily find it. Minus x1 plus epsilon times 1 minus x1 squared times x2. This is the f of the van der Pol oscillator. Okay? Then df dx equals 0, 1. Okay? If you remember. And then you have minus 1 minus epsilon x1 squared. Minus 1 minus 1 minus epsilon 1 x1 squared. And the last element is epsilon times 1 minus x1 squared. You have this guy. Okay? And remember that the origin is an unstable equilibrium point. So the trajectory it's a repulsor like. The trajectories veer off this equilibrium, these simple trajectories. Yeah? They go into dynamics. But where does it go? And now we have to check the results. So number of saddle points. So Poincare. Number of saddle points is 0. Yeah, I remind you here. And number of foci and nodes. S, number of saddle points. Okay, you have this. You've got these two. So S equals 0, hence N equals 1. And indeed, you have one unstable focus or node. One unstable node or focus. Bendixson says that if this is zero, is not zero, and keeps sign, okay, then you have no limit cycle. But look, in this case, for the van der Pol oscillator, df1 dx1 plus df2 dx2 equals what? I don't remember where. Oh, yeah, here. Epsilon 1 minus x1 squared. Well, this is 0 for x1 equal to 1. You see? It's 0 for x1 equal to 1. So there probably there exists a limit cycle. And if this unstable guy, because with the result of Poincaré, we can draw the conclusion. Probably the van der Pol oscillator has a limit cycle. And since the equilibrium is unstable, probably the limit cycle is stable. Probably, of course, there is much more complicated analysis, but we don't go into that because you look at the you may look in the book of Khalil about these things. In the book of Khalil about these things, okay? Yeah, okay. Okay, right. Okay. Well, in the other case of the linear mechanical oscillator, df1 dx1 plus df2 dx2 is minus c over m, if you remember, or minus b over m. Where is it? Yeah, minus b over, oh, but this is not x2. This is b over m like this. Sorry. Yeah, it's minus b over o. This is a mistake here. No, this is a mistake. Sorry, I looked at the wrong picture. Sorry, x2. No, I shouldn't have looked at this one. Not here. Here, sorry, here. So you see here on the diagonal of this guy, there is no limit cycle because this is always negative. This is always negative. Okay, it's always negative. Yeah, and the energy is also bounded. Whereas in the case of the van der Pol oscillator, this is not true. This is not true because this can become zero, can change signs. Okay. Right. Let's look on Maple and check some of these examples and see that what we have just discussed, it's true. Okay. So limit cycles, a crucial nonlinear property. We could understand that such systems do exhibit oscillations. Okay. Do exhibit oscillations. Now I'm trying to open Maple. Okay. Did you manage to understand some of the physics of these things? Can you understand? Hmm? Could you understand some of the physics of the things we discussed here? I'm asking you. Hmm? Okay, can you see my maple screen now? Hmm? Can you guys see my maple screen now?
Yes, I can.
Okay. I was asking you earlier if you could understand a little bit the physics of these things.
I wasn't so confident. So.
You weren't so confident. Okay, things are not very easy, but the physics of it says that if there is an oscillatory behavior, okay, we can get to that with a nonlinear system if you have different types of equilibria, okay? So if the trajectories, you saw the mechanical oscillator, if the trajectories are bounded in a set, okay, then you can either go to an equilibrium point, you can either go to a limit cycle, or you're exactly on a limit cycle. These are the main results, okay? Let's look at the van der Pol oscillator. Maybe things will get, this example will shed some light on things. We have here the equations. Yeah, this is the way the system is defined. Okay, you see here the parameter epsilon. Okay, this is the F. This is the F. You remember F. And this is the Jacobian of F. This is the Jacobian of F. Yeah. Okay. This is the Jacobian of F, right? And here we have the equilibrium points, and we only have the origin as the unique equilibrium point of the system. So the system the only equilibrium point is at rest, so to speak, at rest. And the evaluation of the Jacobian in the equilibrium point is this matrix. Okay? And here we take epsilon to be minus 1/2. Okay? And if you take epsilon negative, then you have a stable equilibrium point. Then you have a stable equilibrium point. Okay? And now we have epsilon negative. Epsilon negative. You can get a stable equilibrium point. Okay? It's a focus if you look closely. It's a focus. Okay? It's a focus. Okay. Now, look when you plot the phase portrait. So the origin in this case is a stable equilibrium point. So the system starts from a limit cycle. If you look, it starts from a limit cycle. Yeah. And then, because it's stable, the limit cycle fades away, and the system is going as a focus towards the equilibrium point. You see? Look here. Stability. This is what happens in this case. Okay? And this is the time evolution of the things. Now let's see what happens when epsilon is negative. When epsilon is negative. Take here plus. Take here plus. And I think this is pretty much it. And now we just run the sheet. See what happens. You see, you have an unstable node in the equilibrium point. You see? You see the oscillatory behavior. How nice. So the origin, look at the real parts. This is the real parts of the eigenvalues of matrix A. They are positive. So this is an unstable focus. This is an unstable focus for positive epsilon. For positive epsilon. Hence, what happens? The system, the trajectories will usually start from somewhere. So if you have very small, you see here the initial conditions are almost zero. Okay, so if you start very close to zero, instead of the system going back to the equilibrium point, the trajectory will go away and stop on the limit cycle. So the system will forever oscillate constantly. The system will forever oscillate constantly. Okay? Very interesting, huh? So this is indeed an oscillator, a structurally stable oscillator. Okay? You can see this here. Epsilon positive, epsilon positive. Okay? The same happens when you plot the solution using ODE plot. Okay, the system goes away from this area, which is close to the equilibrium point, because I took the initial conditions very close to the equilibrium point. Okay, very close to the equilibrium point. And I got this very nice limit cycle. So what does this mean? If you plot each of the solutions of the trajectories x1 versus time and x2 versus time, this is how they look like. They will forever oscillate. They will forever oscillate. Okay, so the equilibrium, that's why we kept saying that the stability of an equilibrium point is a property of the equilibrium point and not a property of the system. Okay, so the origin is an unstable equilibrium point, but the system exhibits structurally stable oscillatory infinite behavior. And this is stable because the system is not broken. The system is not broken. Okay? So who is stable here? If this equilibrium point where things start is not stable, probably the limit cycle itself is stable. The limit cycle itself is stable. So you see, stability is a property of the trajectory and not a property of the system. Do you understand what I'm saying? Because in the same system, you have unstable equilibrium points, so an unstable constant trivial trajectory, and a stable limit cycle. A stable limit cycle. Can you understand what I just said? Does it make sense to you?
Yes.
Yes. Very interesting, don't you think? A simple system like this behaving like an oscillator. Very nice. Let's save this guy. Let's open something else. So let's go through all the examples I have here. I have some problems from a book which I solved here. Oh, also another example is the guy with mu. You remember the system with the coefficient mu. Here we have a negative mu. And here we'd like to see the also we'd like to see the polar coordinates transformation. So this is the system. You recognize it from the slides. Right. This is the vector field F describing the first order type of dynamical system. Good. Equilibrium points. It's very easy to see that the only equilibrium points are the only equilibrium point is the origin. And this is the Jacobian of the system evaluated in the equilibrium point. Okay. As you can see here, it's very interesting. Let's see. Let's go back to the Bendixson-Poincare thing and say AX is the Jacobian of F with respect to the variables x1 and x2. And let's see what happens. Well, I think we have to run the whole business, and then we can look at some things. Okay. So let's go back. So this is the Jacobian. Okay. So let's see if this changes sign. So let's solve the equation. The element 1, 1 of x plus the element 2, 2 of ax, that's the Bendixson theorem. Let's look at that. Note that x1 is that 0 is an equilibrium point. The origin is an equilibrium point, and if you look here, you'll see you have an unstable focus. It's an unstable focus. Look at the eigenvalues of A. This is an unstable focus. Yeah. This is an unstable focus. Okay. What happened? Sorry. This is an unstable focus. All right. An unstable focus. Okay. So you have one focus, no saddle points. So the Poincaré theorem should tell us something. The Poincaré theorem should tell us something. Okay. And now let's check the Bendixson part. The Bendixson part. Poincaré. Yeah, one. Okay. Let's just put it here. Okay. So, and how do we check this? We solve, or we cannot plot. I don't think we can plot, but we can definitely solve. What happens? Solve ax 1, 1 plus ax 2, 2 equals 0 times, do this, x1, x2. Let's see if it does something. Okay, so you see it has solutions. It has solutions. So probably somewhere it will be 0. Somewhere it will be 0. Okay, so if you fix, for instance, x2 equal to 1, say, okay, so there is the possibility of this guy, or x2 very small, you can get 0. So that means it changes signs. So probably we do have a limit cycle. We do have a limit cycle. Now let's pass everything into polar coordinates. If you remember, in polar coordinates, this is how these are the two equations. These are the two equations of the system in polar coordinates. So the radius, which has two equilibrium points, 0 and 1, and the angle, which is constant. The angle, which is constant. Okay. All right. And this is, we plot here the R, the FR. So we plot the FR, which is this equation, versus R, because this is a first order system. This is a first order system. Okay. And we have 3 equilibrium points, -1, 0. Okay, but R is always positive. So we neglect the left part of this graph. So we have R equal to 0 or R equal to 1. So 1 can be an attractor or 1 can be a repulsor. And consequently, 0 can be a repulsor and later can be an attractor respectively. Okay, so it's skew symmetric, so to speak, to the property of R equal to 1. So the eigenvalues here, this is the A matrix of the polar coordinates, and this is the phase portrait, R versus the angle theta. So on the horizontal line is R, the radius, and theta, the angle is on the vertical, and if you can see, in this case, when mu is, I don't know what mu is, negative or positive, something, I think is negative this time. Yeah, so this time when mu is negative, okay, so the radius starts from the initial condition and goes to a constant value. It stops at 1. Okay, and the angle theta keeps growing, keeps turning constantly. Okay, all right, so this is what the radius looks like. It goes from 0 to 1 if you look, and this is the behavior of theta with respect to time. Okay, so what happens again in the classic x1, x2 coordinates? What happens? So what happens is the limit cycle happens. So the system goes away from the origin up to, just like the van der Pol oscillator, up to a limit cycle and stops there forever. Stops there forever. Look at this guy. This is much more clearer. This is much more clearer. And this is the behavior of x1 and x2 with respect to time. Now, let's take mu positive. Let's take mu positive and run the maple sheet and see the results. Okay, see the results. Right. So, when mu is positive, this time, note that the eigenvalues of the matrix A of the original system, matrix A of the linearized of the original system, proves that the origin is a stable focus. Yeah, so this is a stable focus. Look here. This is a stable focus. Again, the Bendix-Poincaré, you can't change that. It shows that somewhere the equation of those two diagonal elements of the Jacobian in X, they change signs because the equation equal to 0 has solutions. So probably there exists a limit cycle. We go back to the polar coordinates, and this time this is the graph of R. This is the picture of FR versus R. So 0 is now an attractor and 1 is a repulsor. 1 is a repulsor. So this means what? Look, this is the phase portrait of theta versus R. Theta goes along the vertical line constantly and is negative. That's what theta does. So the angle, it turns what? If angle is negative, it turns counterclockwise, right? This is counterclockwise or clockwise. How is it? No, it's actually clockwise. No, this is clockwise. Theta is turning clockwise. What does R do? R goes from 1 to 0. So the R is smaller and smaller. The radius is smaller and smaller. So this is a focus behavior. Look, this is R in time, goes from the unstable 1 to the stable 0. And look what happens. The system may start from the limit cycle. It starts from the limit cycle, okay, and then goes very nicely to the origin through a focus. Okay, sorry about that. Through a focus. Okay. Nice behavior we have here. And we prove that using ODE plot as well. And what happens? So in this case, the system is stable, you see. It goes to 0 oscillating. Why oscillating? Because the system is the equilibrium point is a focus and not a node. Okay. So another very nice example of a limit cycle. Let's save this and open something else. And now let's see different other examples. So limit cycle. Let's see what this is about. 3.10. Okay, 3.10. This guy. Again, a polynomial system. Look at this. Look at the equations. Okay. Jacobian. Look at the Jacobian if you add it it's y minus 5. So again, we might have a limit cycle because the Jacobian 1, 1 plus Jacobian 2, 2 equals 0. This has, so we can do this, solve. This has a solution. Okay. Has a solution. Oh, well, on the coordinates x and y. Well, they are, but for some reason it's not working. We should see something. Oh, we don't see anything because we haven't run the maple sheet. Sorry about that. Sorry about that. So if you solve this guy, we have a solution. We have a solution. Okay. So the Bendixson theorem is not observed. The Bendixson theorem. Okay. And these are the equilibrium points. These are the equilibrium points. Okay. These are the equilibrium points of this guy. Okay, so actually it's only one of them. So this is the equilibrium because we talk about real solutions. Okay, we talk about real solutions, not complex ones. So these are all the solutions, but since we talk about equilibrium point, the system has only one equilibrium point. Okay. I'm not sure if we can do the real thing here and ask him to be real. Real. Oh. Okay. Now we evaluate the Jacobian in this equilibrium point. And the eigenvalues, you see, so this is a stable node because both eigenvalues are negative, real and negative. So this is a node. The equilibrium point 0, 1 over 3 is an equilibrium point. Okay. The Bendixson-Poincaré condition, we have it here. We just repeat it because I did it here. So I actually want to repeat this. So I'm going to take this from here and submit it here. Okay. All right. Now we put everything in polar coordinates, and if you go to polar coordinates, the equations are more complicated. The first is the equation for r, and the second is the equation for theta. So now they are not decoupled any longer. So even in polar coordinates, the equations are more difficult to analyze. More difficult to analyze. Okay. Yeah. But it's very interesting. These are the conditions. So with actually r and theta, if you look here, they have only one equilibrium point, or two. Actually, they have two equilibrium points. Okay, they have two equilibrium points, 1 over 3 and half pi, and 1 over 3 and minus half pi. They have two equilibrium points. Okay, so this is the phase portrait. The phase portrait of the polar coordinates, or no, oh no, this is the phase portrait of the original system. Okay, so no limit cycle here, even if we showed that the condition about limit cycles was fulfilled, the Bendixson. So Bendixson said there is the possibility of having limit cycles. Okay, there is the possibility of having limit cycles. That doesn't mean we actually have them. And actually, and then the original point is just a simple node. A simple node. So we could not find a limit cycle in this guy. We could not find a limit cycle in this guy, even if the Bendixson Poincaré shows that there is a solution when it goes to 0. Okay, all right, but this guy does not exhibit a limit cycle. Okay, another guy. This one. So we have a stable focus, as far as I can see, but actually we have a saddle point here. So what do we see here? There are more equilibrium. Oh yeah, we have more equilibrium points. Okay, so again, just like the mechanical oscillator, if you remember, just like the mechanical oscillator, okay, we do have here multiple isolated equilibrium points, the origin and two other constant equilibrium points. Okay, two other constant equilibrium points, right? So the origin is a saddle point, apparently. The origin is a saddle point. So if you see, it's not going to the saddle point. It goes away from the origin. The system goes away from the origin. Goes away from the origin. Okay, look, and it stops somewhere at the other equilibrium points. The other equilibrium points. I suppose we have a discussion also about these parameters. I'm not sure if we can change this behavior, changing the parameters, for instance. You see what I mean? So let's change this and see what happens. Whoa. So weird things happen. So one of them is stable and the other one is unstable. Okay, so this looks like some very strange. Okay. I'm trying to see if I can get it to behave with the limit cycle. You see? Well, not much happens. This is very strange behavior. Let's take this one negative and the other one positive. Now this is unstable as well. This is unstable as well. So this is an unstable node. Very interesting. Unstable node. You see, this is diagonal. Look, the situation, diagonal. If you remember, diagonal, those are straight lines. When you have diagonal, the phase portrait is a straight line. When you have diagonal behavior. Okay, let's take this one negative and see what happens. Okay, so now we have stable behavior. This is also a node. This is a stable node. Look, it's a stable node. Look where it goes. And again, we have the stable degenerate node with A being a diagonal matrix. Okay, so the most interesting part, so we don't have a limit cycle. We cannot see a limit cycle, although probably the Bendixson properties are not necessarily, they are probably not observed. Okay, they're not observed, I suppose. Another example, this one. Now this is interesting with an absolute value. Look at this one. This has also a sign issue here. Also has a sign. Look at the Jacobian this time. Look at the Jacobian this time. Okay. Equilibrium points. Again, we have three isolated equilibrium points with this guy. And we have some sort of, you see, this should be a center behavior. Because look, the real parts are almost zero. Look at this guy. Look at A. Real part almost zero. But it's never, this is the perturbation we discussed about earlier. This was supposed to be a center behavior. But it's not a center behavior. It's going to be a focus. Because you have this very small perturbation in the real part. So they don't just actually sit tight and precisely on the imaginary axis, okay, on the imaginary axis. So the center is not a structurally stable behavior. Look here as well. Yeah, the question is this, if this is has a limit cycle, the conditions need to be checked. The conditions need to be checked. Apparently, there should be some limit cycle. Let's see what happens if you just increase this number. Yeah, it's actually a limit cycle if you look closely. The behavior is on a limit cycle. Yeah, it's a limit cycle. You see? It's not a center, but a limit cycle. So, very interesting, huh? The behavior should be a center, but it's not. And even degenerate as it is, or even disturbed as it is, and not robust, from the center, the behavior goes to a limit cycle, apparently. Okay? Apparently. Probably, if you look at these equations, you cannot have zero because of the absolute value here. Because of the absolute value here. This will never be zero. So the sign will not change. So probably, or there exists a solution of this guy. No, because it's absolute value. No, this guy has a solution. This guy has a solution. So probably we do have a limit cycle. We have 3 points. We have 3 points. One of them is stable, the other are not. Okay. So this is the kind of analysis. This is the kind of analysis. Look at these equations. You see, this is x to the power 3, and here you have absolute value. Okay, so this exhibits very nice oscillatory behavior in terms of a limit cycle. In terms of a limit cycle. Yeah? Very interesting. Yeah. So simulation is very helpful. That's what I'm saying. Simulation is very helpful. You know, this is apparently another mechanical system because it looks like something containing a pendulum. Limit cycle again. Okay, limit cycle. Look, but this is stable and the limit cycle is unstable, so it starts with an oscillation behavior and it fades away and goes to zero. So unstable limit cycle this time. Unstable limit cycle this time. Okay, and the analysis is done using these parameters here. This looks like a little bit like the pendulum. Okay. 3.6. What is this guy? Well, this is very interesting. Now look at this system. This has very difficult equations. If you look here, you have the discontinuities. Okay, here you have discontinuities. Look at the phase portrait. Very interesting. Very interesting phase portrait. Okay. Now it behaves with a limit cycle. Look, unstable behavior, going away and stopping and constantly oscillating on a limit cycle. Okay. All right. Very interesting, this example as well. I think we only have 2 more. Oh, this looks weird. Again, limit cycle. Look at this example. Polynomial. Okay. This Bendixson-Poincaré has a solution, so we do have probably a limit cycle. The origin is the only equilibrium point, but the origin is probably unstable. Yeah, it's an unstable focus. Look here, the origin. So if it's an unstable focus and there is the possibility of a limit cycle in this bounded set, it goes to the limit cycle. Look at this one. This is much nicer. Okay, so constant, very nice, constant oscillations. And the last one, okay, the last one as well, a much simpler example. This is constantly oscillating if you look closely. Let's see if this is a center behavior actually, which turns into a limit cycle, because this could be the case. This could be the case. No. So we have, oh yeah, we have 3 equilibrium points. Once again, we have 3 equilibrium points. The last one is a saddle point, so probably, sorry, probably the first, no, probably the second and the third equilibrium point. These isolated guys. This looks like the mechanical oscillator, you see? So the behaviors are similar if you look closely. The behaviors are similar. That means that the mechanical oscillator and the pendulum are benchmark examples. Okay, right? So, yeah, we do have. So why should we have what I'm interested in? Sorry, is why is this? Why is this a saddle point? Eigenvalues of oh, okay, yeah, it makes sense. Sorry, it's okay. Oh, but the origin, as expected, the origin is a center, so the origin is undecidable. What should the origin be? What should the origin be? Very interesting. So 1, 0 and -1, 0 are saddle points, and the origin is something we don't know. Saddle points are unstable, so how should the origin be? If 1, 0 and -1, 0 are unstable saddle points, how is origin supposed to be? How's the origin? How's the origin? If the other two are remember the mechanical oscillator, if the other two, okay, I can't because it's a different computer. I can't make a drawing. I can't draw this. But let's think. Saddle point is unstable, so the behavior goes away. So probably the origin and those 2 saddle points can bring us, or the saddle points can separate the phase plane in 2 areas: the area with the trajectories, with the origin, and the rest. Okay, just remember the drawing of the mechanical oscillator. So if the saddle points are unstable, the third one, which is the last one, the origin, how should it be? Stable or unstable? What do you think? Hmm? How should it be? How should it be? How is 0 if the other two are unstable? Hmm? Come on, it's not that difficult. Think about the physics. How should it be?
Maybe stable.
Probably stable, of course. So, because we said the behavior around the origin is a center, so it's undecidable. I don't know whether it's stable or not, but the other two are saddle points, so probably this one is a stable guy. Himself, that's the question. We don't know that, but we know there is a limit cycle. We know there is a limit cycle. So probably it's a limit cycle around it. So the origin is stable in the sense that around it we have a limit cycle because we don't know the center behavior, whether or not it's stable. We showed in the previous example, indeed. So this is what it looks like. This is what it looks like. It's a center, indeed. It's a center, indeed. Okay. Not a center, sorry, a limit cycle, indeed. Yeah, this is a limit cycle, indeed. Limit cycle. Yeah, very interesting. Very, very interesting. So this is a limit cycle by all means. You see, the analysis is qualitative. Okay, is qualitative. Okay, is not quantitative. It's hard to compute and say things precisely because most of the conditions we make here, or most of the conditions we enforce here, are unfortunately most of the conditions are sufficient and not necessary, I'm afraid. Okay, so it's not an if and only if. It's not an if and only if. You see, look here, wonderful picture. Okay, so I invite you to study these examples yourselves. Okay, and see what happens. See what happens. Yeah. We have here also the pendulum studied. So the classical pendulum this time. We have the classic pendulum this time. We know that when the pendulum has friction, the pendulum hanging will stop. The equilibrium point is 0, 0. Okay, and its equivalent forms with pi with k pi 0. These are the stable equilibrium points. Hence, can we have a limit cycle? That's the question in the pendulum. Can we have a limit cycle? Well, no, because df1 and df2 is always non-zero. Look here. df1 x1 plus df2 x2, so the Bendixson condition is satisfied, is constant and non-zero. So the pendulum will never ever have a limit cycle, even if you have friction or not. When friction is not present, of course, the behavior of the origin looks like a center, so probably it will constantly swing when you have no friction. But that's not the case, because no matter if you have a little bit of friction, infinitesimal, even 10 to the power minus 5, you will go to a stable focus. Okay, so the pendulum never exhibits a limit cycle, I'm afraid. Will never ever exhibit a limit cycle. Okay? So we can see the differences between several classes of second-order systems. Okay, second-order systems. The systems of the type pendulum, with foci and nodes and no possibility of showing constant oscillation, and the systems such as mechanical oscillator, which again may exhibit no limit cycle, that will never oscillate, okay, because there's always a little bit of friction due to the environment, and not only that, okay. And then there is the systems, the polynomial ones, of the type van der Pol oscillator, which exhibit constant oscillations. Constant oscillations. Even in a parallelogram separated by some saddle points, even if you don't have this separation, the limit cycle is there. Okay? And those systems, like I said, sometimes can be very, very useful, because those are what we call structurally stable oscillations. Structurally stable oscillations. Okay. Question. Okay, so I invite you to look in the book of Khalil for further details if these things are not very clear to you right now. I also invite you to do the assignments. Did you try the assignments? Any of them so far? Have you tried anything? Any of the assignments so far? Sorry?
I tried the first one.
I can't hear you very well. Can you speak?
I tried the first one.
Oh, you tried the first one. Very nice. I'm going to check. Yeah, let me check right now. Let me check right now and see if I see something over there. So the first one, assignment 1. Participants 2. Oh, so 2 people have submitted. Wonderful. So I need to grade you. This is music to my ears, like the English says. Okay, thank you. So please try to do the second one. Is the second one open? Let's check. Okay, if it's whether it's open or not. We are today 8th of November, right? Oh, so it's open. The second assignment is also open. So please try, be kind, and solve the second assignment as well, okay? Please do that. Would this have... Sorry? What were you saying? Huh? Were you saying something?
Can I ask another question?
Yes, please.
I didn't hand in anything yet because I was sick last week, or I'm still sick. So the problem is I'm not really working on it right now.
No worries. Okay. So I decided to leave the assignments open until the end of the lecture. So you people will have enough time until January, but in January, I'm announcing it, I'm closing it. Okay, so if you do not submit in January until the end of the semester, it's not nice. Agreed?
Yeah, of course. Like I will work on it, because if you don't work on it, I think it will be hard to follow the lecture any longer if you don't do something practical.
Yeah, that's true. I'm showing you some files. You can work them out yourselves. These files, these examples I'm showing you, they are all on Moodle and on Teams. So you can download them. You can run them in Maple and draw your own conclusions. You can do these examples yourselves in MATLAB. If you do not understand Maple, you can repeat these examples in MATLAB. The code is very easy. I showed you several times the code to do numerical integration in MATLAB. And you also have the code on Teams and on Moodle. So please download the codes and transfer the examples I show you in Maple, transfer them in MATLAB. You can do that, can't you? It's not very difficult. And then you can do the assignments. So I think it's more than reasonable from my side to leave the assignments open until the end of the semester, all the assignments, okay? But at the end of the semester, I'm going to close the assignments, okay? So I think 2.5 months is enough time to do 4, I'm not going to say lousy assignments. You can do that until January, can't you? Okay. Is this all right with you?
Yeah, it's fine for me. I just yeah.
Okay. If you have any questions, if you have questions about the assignments, about the lectures, about the examples I show you, please feel free to contact me anytime and we can discuss. We have 4 hours every week, so we have enough time to discuss anything I can help you with. Okay? I'm open for discussion. Please do consult the notebook, the OneNote notebook, which is always there with the notes and everything. Please consult and use and check Moodle and all the materials on Moodle. Okay? And please start to look through the papers you are required to study for the examination. And please let me know in due time which papers you selected for the exam report and presentation. Okay? Is it understandable? Please start selecting the papers you want to do for the exam. You can write to me on Teams. I select this paper and this paper. You have numbers. All the papers for the exam, the set of papers is numbered from 1 to 11 or 13. And you say, I pick paper 1 and 7. I pick paper. You can pick 1, you can pick 2, 3, whatever.
Okay, and how is it going to work then later? Do we need to summarize it, or how will
it at the exam date? So either in the last lecture or at the exam date, so in January or probably at the end of the semester, I'm leaving open, I'm opening the exam, so to speak. So if you want to do it before the exam period, okay, before the exam schedule, you can do it, or you can do it on the exam date, because we are going to set a date for the exam at the end of the semester. Okay? So it's your choice. It's your choice. If you want to do it in advance and you think you understand, fine. If you want to do it at the exam date, we can do it at the exam date. And we are going to do it orally. Okay? So you submit a written report to me, and then you present what you understand. We talk about it, and I'm going to ask you questions, and you're going to show me the simulations of that particular paper, okay? And we are going to discuss about it, and then you get a grade for that, okay? And the grade is going to be added to the assignments, and you get the final grade. Does it make sense to you?
Yes.
Cool. I like it when everything makes sense. I do love it like that. Okay, so I think it's 6:30. No, sorry. This is. I'm going to ask Florian something very, very, very funny. How do you tell the half hour in German? Do you say it like 30 minutes to 6, or do you say 30 minutes over 5 or something like that? How do you express?
It depends on which part of Germany you are in. Like I'm from the eastern part, and we say like maybe like 15 minutes before this and that, or 3:30 means like 15:30 is like 4:30 or 3 p.m.
Okay. I understand. So in the eastern part, you say it like that, but the western?
They do it the other way around. They say like it's
quarter past.
Yeah, they are using the other method, and it was quite funny when I like met some students at my home university who were like from the western part. They didn't understand at first sometimes if you were talking to them, because they were like, "Which do you mean right now with that?" So yeah.
Yeah, makes sense. No, I was saying because I was just on the verge of making the mistake. Also, the Dutch say it like you do in the East. They say half an hour before. You know, and when I was in the Netherlands, it was very difficult for me because I always thought it's 1 hour extra, you know. So I actually missed the train like that. So yeah, no, so now it's 5:25. That's the English way. So I think it's enough for today. So if you have any questions or comments, please feel free. I'm listening. I understand. Look, I'm totally sympathize with you that this is not very easy what we talk about here, but this is a research master class. So I know, I probably think you expected it not to be easy. But I'm trying to make it as simple as possible for you, looking at physics. So, okay, again, if you have questions or comments, please. Next week, we are going to discuss the general case of nth order system and introduce the notions and the very nice results of Lyapunov stability. Okay. And then we'll have an application of Lyapunov stability, and then we probably, if we have enough time, we'll talk about feedback linearization. Okay. This is the plan for the rest of the lectures. Well, if nothing else, then I'll see you guys next week. Thanks for attending.
Thank you. Goodbye.
Thank you. Goodbye, teacher.
Cheers, everyone. Bye.
Thank you. Have a nice evening.
You too.